For the last century, astrophysicists have been working backward. We've mapped the cosmos from our bustling cities today, past ancient galaxies, all the way back to the explosive birth of the universe. Through decades of intense observation, we built a sturdy mathematical framework to explain how all of this fits together. The standard model of cosmology served as the reliable blueprint for reality. To test this blueprint, scientists rely on a specific measurement known as the Hubble constant. Think of it as a cosmic speedometer that tells us exactly how fast the universe is expanding right now. Look at this timeline charting the expansion from the early universe to today. Based on the oldest cosmic background radiation we can measure, our physics predict the speedometer should be locked at 67 kilometers per second per megaparsec. Getting that exact number from our physical observations is the ultimate verification. It confirms that our math works and that we truly comprehend the mechanics of the cosmos. The problem arises when we stop looking at the ancient cosmic background and start measuring the expansion happening in our own neighborhood, using exploding supernovae in nearby galaxies. As this diagram shows, when we calculate the speed using those nearby local measurements, the red indicator hits 73. It pushes past the blue baseline, creating a glaring mathematical contradiction. A difference of 6 or 7 units sounds like a tiny rounding error, but on a cosmic scale, a gap this wide means two perfect rulers are giving us different lengths for the exact same object. Astrophysicists call this discrepancy the Hubble tension. Our two most reliable ways of observing the universe are in conflict, and both sets of data are coming from our most trusted instruments in orbit. This leaves us with an uncomfortable dilemma. Either the billion-dollar telescopes we rely on are feeding us flawed data, or the actual laws of physics are wrong. For years, the scientific community assumed this gap was a simple error in observation. The hope was that as we build sharper, more capable telescopes, the measurements would naturally align. But as we look toward 2026, a series of international studies are projected to deliver the most precise expansion measurements ever recorded. This graph tracks those historical measurements over time. Notice what happens at the end of the timeline. Instead of converging, the red and blue trend lines violently split further apart precisely at the 2026 data point. When measurements reach this level of consistency across different teams, the traditional excuse of mechanical error vanishes. The discrepancy is no longer a glitch, it is a feature of the universe. This data transforms a mathematical oddity into a full crisis, applying unbearable stress to the entire structural integrity of the standard model. The weight on those old models is only getting heavier, particularly with the flood of new data bouncing off the gold-coated hexagonal mirrors of the James Webb Space Telescope. When the JWST peered into the very early history of the universe, it found massive, fully formed galaxies. According to the current laws of physics, there hasn't been enough time in the lifespan of the universe for these structures to grow. These structural impossibilities lead right back to dark energy, the unexplained force responsible for accelerating the cosmic expansion. It makes up roughly 68% of the entire universe, yet its exact physical nature remains a total blind spot. Observing this mounting pile of conflicting evidence, experts at institutions like the Keck Observatory are beginning to voice a very real alarm. As Keck's chief scientist John O'Mara summarized the situation, given the flawless contradictory data, the impossible galaxies, and the invisible forces, cosmology as we know it may be broken. The scientific community is largely accepting that we can no longer patch the holes in our current framework. We have crossed into a landscape of deep uncertainty. To make sense of the expanding universe, researchers are proposing radical solutions. Many believe we need a complete, ground-up rewrite of the standard model. This means taking a hard look at the bedrock of modern astrophysics. We may actually need to modify Albert Einstein's original theory of gravity to account for these massive anomalies. It forces us to confront a humbling reality. No matter how advanced our orbital hardware gets, the cosmos is still guarding fundamental secrets we do not comprehend. The breakdown of the current model reveals a universe that is far more complex than we ever predicted. In the timeline of this discovery, 2026 marks the point where we stop trying to fix the old model and start looking for something entirely new. So what do you think? Are our core laws of physics completely wrong? Share your own theories down in the comments below. If this documentary changed your perspective on the space around us, please hit the like button and share it with someone who loves a good scientific mystery. Make sure to subscribe to Prism Horizon and turn on the notification bell so you don't miss our upcoming deep dives into the dark corners of the cosmos. Thanks for watching. Keep questioning everything, and we'll see you in the next one.